Welcome! In this session, we'll tackle the problem number 1749, maximum absolute sum of any subarray. This problem is a great way to deepen your understanding of array manipulation and algorithm optimization. Let's dive in and explore how to approach this challenge step by step. The problem requires us to find the maximum absolute sum of any subarray in a given integer array nums. A subarray is any contiguous portion of the array, and the absolute sum refers to the absolute value of the sum of the elements in that subarray. The task is to return the largest absolute sum that can be achieved from any non-empty subarray of nums. The input is an integer array of length n, where n can go up to 100,000, and each element of the array lies between -10,000 and 10,000. The output is a single integer representing this maximum absolute sum. For example, consider the input array 1, -3, 2, 3, -4. In this case, the output is 5, and here's why. The subarray 2, 3 has a sum of 2 plus 3 equals 5, and this is the highest absolute sum we can achieve. Another subarray, -3, has a sum of -3, but its absolute value is only 3, which is less than 5. Thus, the maximum absolute sum for this example is 5. Now let's look at another example with the input array 2, -5, 1, -4, 3, -2. For this array, the output is 8. To understand this, consider the various subarrays. The subarray 2 has a sum of 2, while the subarray -5, 1, -4 has a sum of -8. Taking the absolute value, we get 8, which is the highest absolute sum for any subarray here. Another subarray 3 has a sum of 3, but that's still smaller in magnitude compared to 8. Finally, let's consider an example where the array contains only negative numbers, such as -1, -2, -3, -4. For this input, the output is 10. The subarray -1, -2, -3, -4 itself has a sum of -10, and its absolute value is 10. Any other subarray, such as -1, -2, or -3, -4, results in a smaller absolute sum. Therefore, the maximum absolute sum is 10. In summary, the problem challenges us to account for various scenarios, including arrays with all positive numbers, all negative numbers, a single element, or alternating positive and negative numbers. For example, in cases like 2, -5, 1, -4, 3, -2, the maximum absolute sum depends on finding the subarray that balances these variations most effectively. To tackle the problem of finding the maximum absolute sum of any subarray, we started by exploring a few approaches. The first is the brute force approach, which is conceptually straightforward. Here, we generate all possible subarrays of the input array and calculate the sum for each one. By comparing their absolute values, we can identify the maximum absolute sum. However, this approach is computationally expensive. With n squared subarrays to consider and n time to compute each sum, the overall complexity becomes n cubed, making it impractical for large inputs. Next, we considered an optimized approach based on Cadon's algorithm. The key insight here is that the maximum absolute sum of a subarray depends on two scenarios: the maximum subarray sum, which is positive, and the minimum subarray sum, which is negative, and its absolute value might be even larger. Instead of examining all possible subarrays, Cadon's algorithm lets us efficiently compute the maximum subarray sum. By applying the same algorithm to the negative of the array, we can also determine the minimum subarray sum. This leads to a much faster solution, which we'll describe in detail shortly. The optimized approach based on Cadon's algorithm can be broken down into 3 steps. First, we apply Cadon's algorithm to compute the maximum subarray sum, which we'll call max_sum. Then, we apply Cadon's algorithm again, but this time to the negative of the array, to find the minimum subarray sum, which we'll call min_sum. The final result is the larger of these two values, either max_sum or the absolute value of min_sum. This is because the absolute sum of any subarray must be determined by one of these two extremes. Cadon's algorithm has a time complexity of n, and since we use it twice, the overall complexity remains n. This makes it an optimal choice for solving the problem. Additionally, we briefly explored an alternative approach based on prefix sums and a sliding window technique. By using the difference between two prefix sums to calculate subarray sums, we can keep track of the running prefix sum and the minimum prefix sum seen so far. This allows us to compute the maximum subarray sum, and by repeating the process for the negative array, we can find the absolute minimum subarray sum. While this method also operates in O(n) time, it requires additional bookkeeping, which makes it slightly less intuitive than Cadon's algorithm. Ultimately, we decided to use the optimized Cadon's algorithm approach as our final solution. The decision was guided by several key observations. First, the maximum absolute subarray sum is determined by either the maximum positive sum or the maximum absolute negative sum. Cadon's algorithm provides an efficient way to compute both values in linear time without needing to explicitly generate subarrays. Compared to the alternatives, the brute force approach is clearly too slow, with its O(n)³ time complexity making it infeasible for larger inputs. While the prefix sum approach is also O(n), Cadon's algorithm is simpler to implement and better suited to this specific problem. It directly computes the maximum subarray sum and can be easily adapted for the negative case, resulting in a clean and efficient solution. The trade-offs are minimal. While the prefix sum approach might be more versatile in problems requiring additional context about prefix sums, Cadon's algorithm is more specialized, making it the ideal choice here. This solution has a final complexity analysis that confirms its efficiency. The time complexity is O(n), as Cadon's algorithm is applied twice, once for the original array to find the maximum subarray sum, and once for the negative of the array to find the minimum subarray sum. The space complexity is O(1), as no additional data structures are used, we only need a few variables to keep track of the sums during the computation. This combination of linear time and constant space makes the approach optimal for the problem constraints and ensures it can handle large inputs efficiently. In this problem, we are tasked with finding the maximum absolute sum of any subarray in a given integer array, nums. A subarray is simply a contiguous portion of the array, and the absolute sum means we consider the absolute value of the subarray sum. To solve this efficiently, we use an extended version of Cadon's algorithm. Initially, we define key variables, max_sum and min_sum to track the largest and smallest subarray sums we encounter, and current_max and current_min to track the running subarray sums ending at the current index. These will help us decide whether to extend our subarray or start fresh at each step. The algorithm begins by iterating through the array. For each element, we update current_max to be the greater of the current element or the sum of the current element and the previous current_max, ensuring we always track the best possible subarray ending at this point. Similarly, we update current_min to track the smallest subarray sum ending at this point. With these values updated, we then adjust max_sum to be the maximum of itself and current_max. This ensures we are always tracking the global maximum subarray sum found so far. We follow a similar process for min_sum, updating it to the minimum of itself and current_min for each element. Once the iteration completes, we calculate the result by comparing the absolute values of max_sum and min_sum. The maximum of these two values is the final result, as it represents the largest absolute sum of any subarray. This approach leverages the efficiency of Cadon's algorithm, which is a dynamic programming technique that guarantees an O(n) runtime. By extending the algorithm to track both maximum and minimum subarray sums, we ensure that we capture both significant positive and negative subarray sums. This is important because the absolute sum depends on both extremes. Some critical edge cases include single-element arrays, where the result is simply the absolute value of that element, and arrays that contain all positive or all negative numbers, where the solution corresponds to either the sum of all elements or the largest negative element in absolute terms. Arrays with zeros also require attention, as zeros do not affect the sum but must still be processed during iteration. The algorithm achieves all of this while maintaining a space complexity of O(1), as it only uses scalar variables to store intermediate results. This space efficiency stems from the fact that no additional data structures are used to cite from the input array nums. The algorithm updates variables like max_sum, min_sum, current_max, and current_min in constant time during each iteration. Let's look at the Python implementation. The function max_sum begins by initializing the tracking variables, max_sum, min_sum, current_max, and current_min, all set to 0 initially. We then iterate through each element of the input array nums. For each number, we calculate the new current_max and current_min by comparing the number itself with the sum of the number and the respective running total. This step decides whether to extend the current subarray or start fresh. After updating these values, we adjust max_sum and min_sum to ensure they record the largest and smallest subarray sums encountered so far. Finally, the function returns the maximum of max_sum and the absolute value of min_sum. This implementation is highly efficient, with a time complexity of O(n), due to the single traversal of the array, and a space complexity of O(1), due to the use of constant auxiliary space. Analyzing the complexity further, the time complexity is linear because we iterate through the array once, and each operation inside the loop is performed in constant time. The space complexity is constant, as we only maintain a few scalar variables regardless of the size of the input array. To solidify our understanding, let's walk through an example. Consider the input array nums equals 1, -3, 2, 3, -4. Initially, all our variables are set to 0, max_sum equals 0, min_sum equals 0, current_max equals 0, current_min equals 0. Starting with the first element, 1, we calculate current_max as the maximum of 1 and 0 plus 1, which results in 1. Similarly, current_min becomes the minimum of 1 and 0 plus 1, which is also 1. We then update max_sum to the maximum of itself and current_max, resulting in 1, while min_sum remains unchanged at 0. Next, for the second element, -3, we calculate current_max as the maximum of -3 and 1 plus, -3, which is -2. For current_min, we take the minimum of -3 and 1 plus, -3, resulting in -3. We then update max_sum to the maximum of 1 and -2, which remains 1, and min_sum to the minimum of 0 and -3, which becomes -3. Continuing through the array, we repeat these steps for each element. By the end of the iteration, we find that max_sum is 5, which corresponds to the subarray 2, 3, and min_sum is -4, which corresponds to the subarray -4. The result is then calculated as the maximum of max_sum and the absolute value of min_sum, giving us max 5 abs -4 equals 5. This demonstrates how the algorithm efficiently computes the maximum absolute sum of any subarray in linear time and constant space while handling both positive and negative extremes effectively. This implementation efficiently solves the problem using an extension of Cadon's algorithm. The goal is to find the maximum absolute sum of any subarray in the input list. First, we initialize variables max_sum and min_sum to track the maximum and minimum subarray sums encountered so far. Similarly, we set current_max and current_min to 0, representing the current sums as we iterate through the array. These variables allow us to dynamically compute the maximum and minimum subarray sums ending at each position. Within the loop, for each number in the array 1, we calculate current_max as the maximum of the current number alone or the sum of the current number with the previous maximum subarray sum. This ensures we either start fresh with the current number or extend the existing subarray. 2, we update max_sum to be the largest value between its current value and current_max. Similarly, we calculate current_min as the minimum of the current number alone or the sum of the current number with the previous minimum subarray sum. This tracks the smallest subarray sum ending at the current position. We then update min_sum accordingly. Finally, the result is the maximum of the absolute values of max_sum and min_sum. This ensures we account for both positive and negative extremes of subarray sums. The algorithm runs in O(n) time, as we traverse the array only once, and uses O(1) space, as it requires only a few variables. This makes it highly efficient and suitable for large input sizes. This is the Java implementation of the maximum absolute sum of any subarray problem. It mirrors the logic of the Python solution, using variables to track the maximum and minimum subarray sums while iterating over the array. Key differences include Java's type declarations, the use of math.max and math.min for comparisons, and the absence of Python-specific constructs. The solution ensures optimal performance with O(n) time complexity. To solve this problem, we start by initializing four variables, max_sum and min_sum, both set to 0, and current_max and current_min, also set to 0. These help us track the maximum and minimum subarray sums as we iterate through the array. Taking the first number, 1, we update current_max as the maximum of 1 and the sum of current_max plus 1, which gives 1. Similarly, max_sum becomes the maximum of the previous max_sum, 0, and current_max, resulting in 1. For current_min, we calculate the minimum of 1 and the sum of current_min plus 1, which is also 1. Since min_sum tracks the smallest value, it remains 0. Moving to the next number, -3, current_max updates to the maximum of -3 and the sum of current_max plus -3, which results in -2. Max_sum remains 1 because it's greater than -2. For current_min, we calculate the minimum value between -3 and the sum of current_min plus -3, which gives -3. This updates min_sum to -3, as it's the smaller value. Next, with the number 2, current_max updates to the maximum of 2 and the sum of current_max plus 2, which results in 2. Max_sum is updated to 2 since it is now larger than the previous max_sum of 1. For current_min, we calculate the minimum between 2 and the sum of current_min plus 2, which gives -1. However, min_sum remains -3 because it is smaller. When processing 3, current_max becomes the maximum of 3 and the sum of current_max plus 3, which gives 5. Max_sum then updates to 5. For current_min, we calculate the minimum of 3 and the sum of current_min plus 3, which results in 2, but min_sum remains -3. Finally, with -4, current_max becomes the maximum of -4 and the sum of current_max plus -4, which results in 1. Max_sum stays 5, as it's greater than 1. For current_min, the minimum of -4 and the sum of current_min plus -4 gives -4, updating min_sum. The result is the maximum of the absolute values of max_sum and min_sum, giving max, 5, 4, which is 5. Now, looking at a second example where nums is, -2, -1, -3, we again initialize max_sum, min_sum, current_max, and current_min to 0. With -2, current_max becomes the maximum of -2 and the sum of current_max plus -2, which is -2. Max_sum remains 0 because it's larger than -2. For current_min, we calculate the minimum of -2 and the sum of current_min plus -2, which gives -2. Min_sum updates to -2. Then, with -1, current_max becomes the maximum of -1 and the sum of current_max plus -1, which results in -1. Max_sum still remains 0. For current_min, the minimum of -1 and the sum of current_min plus -1 gives -3, updating min_sum to -3. For the number -3, current_max updates to the maximum of -3 and the sum of current_max plus -3, which results in -3. Max_sum remains 0 because it's still larger than -3. For current_min, we calculate the minimum of -3 and the sum of current_min plus -3, which is -6. This updates min_sum to -6. The final result is calculated as the maximum of the absolute values of max_sum and min_sum, which gives max, 0, 6, resulting in 6. Finally, let's analyze a third example where nums is 2, -1, 4, -2, 1. As before, we initialize max_sum, min_sum, current_max, and current_min to 0. For the first number, 2, current_max updates to the maximum of 2 and the sum of current_max plus 2, which results in 2. Max_sum also becomes 2. For current_min, the minimum of 2 and the sum of current_min plus 2 is 2, so min_sum remains 0. When processing -1, current_max is calculated as the maximum of -1 and the sum of current_max plus -1, which gives 1. Max_sum remains 2 as it's larger than 1. For current underscore min, the minimum of -1 and the sum of current underscore min plus -1 results in -1, updating min underscore sum to -1. With 4, current underscore max becomes the maximum of 4 and the sum of current underscore max plus 4, which is 5. Max underscore sum updates to 5. For current underscore min, the minimum of 4 and the sum of current underscore min plus 4 results in 3, so min underscore sum stays -1. Next, with -2, current underscore max becomes the maximum of -2 and the sum of current underscore max plus -2, which gives 3. Max underscore sum remains 5 because it's larger. For current underscore min, the minimum of -2 and the sum of current underscore min plus -2 results in -2, updating min underscore sum. Finally, with the number 1, current underscore max updates to the maximum of 1 and the sum of current underscore max plus 1, which gives 4. Max underscore sum remains 5 as it's greater than 4. For current underscore min, the minimum of 1 and the sum of current underscore min plus 1 results in -1, so min underscore sum remains -2. The final result is determined as the maximum of the absolute values of max underscore sum and min underscore sum, which gives max, 5, 2, resulting in 5. This process demonstrates how we can efficiently calculate the maximum absolute sum of any subarray using a single pass through the array while keeping track of both the maximum and minimum subarray sums. The time complexity of this solution is O(n), where n is the length of the input array nums. This efficiency comes from the fact that we process the array in a single loop that runs exactly n times, iterating through each element once. During each iteration, we perform constant time operations, such as updating current underscore max and current underscore min using simple formulas that involve a comparison and addition. Similarly, updating max underscore sum and min underscore sum involves comparing their current values with those of current underscore max and current underscore min, which are also O(1) operations. Since all these updates occur in constant time and are repeated n times, the overall time complexity remains linear, or O(n). This holds true for all cases best, average, or worst, because the algorithm always processes each element of the array once, regardless of the input values. Now, let's consider the space complexity of the solution, which is O(1). This means the algorithm uses a constant amount of extra space, no matter how large the input array nums is. The space usage is limited to a few scalar variables, namely max underscore sum, min underscore sum, current underscore max, and current underscore min, all of which occupy constant space individually. Importantly, the algorithm does not require any additional data structures, such as arrays or hash maps, to store intermediate results. The input array nums is only read from and not modified or copied, so it does not contribute to the extra space complexity. As a result, the total space usage remains constant, or O(1), making this solution very space efficient. To understand the efficiency of the optimized approach, let's compare it to a brute force method. A naive solution would involve calculating the sum of all possible subarrays of nums and then finding the maximum absolute sum among them. Depending on how the subarray sums are computed, this could lead to a time complexity of O(n)² if prefix sums are pre-computed, or O(n)³ if nested loops are used directly to calculate each subarray sum. In contrast, the optimized solution applies a Cadon's algorithm-inspired technique, which calculates the maximum subarray sum and minimum subarray sum in a single pass through the array. This eliminates the need for nested loops or pre-computations, reducing the time complexity dramatically from O(n)² or O(n)³ to O(n). Mathematically, this is derived from the fact that the loop runs n iterations, and each iteration involves only O(1) operations, leading to a total time complexity of O(n). The space complexity remains constant, or O(1), as no additional memory is used beyond a few scalar variables. The optimized approach is not only more efficient but also far better suited for handling large input sizes. The brute force solution quickly becomes computationally infeasible as the size of the input array grows, due to its quadratic or cubic time complexity. In contrast, the optimized solution processes the array in linear time, making it scalable and practical for real-world scenarios where input sizes can be very large. This efficiency, combined with its constant space usage, highlights why the optimized method is superior and a robust choice for solving this problem. When solving this problem, there are a few common mistakes you'll want to avoid. First, many people confuse the maximum absolute sum with the maximum subarray sum. While Cadon's algorithm can efficiently find the maximum subarray sum, it doesn't account for the possibility that a negative subarray might produce the largest absolute value. Ignoring the minimum subarray sum in magnitude can lead to an incomplete solution. Another mistake is using brute force approaches, where you calculate all possible subarrays directly. This is highly inefficient for larger inputs, as it can take n superscript 2, or even n superscript 3 time, which is impractical for arrays larger than a few thousand elements. Additionally, edge cases can trip up even experienced coders. For example, arrays with all positive, all negative, or just one element, or arrays containing zeros, need special attention. Overlooking these cases can result in incorrect outputs or runtime errors, so make sure to test thoroughly. Another pitfall is overcomplicating the solution by attempting to directly calculate absolute sums for all subarrays. This adds unnecessary complexity and can be avoided by using Cadon's algorithm to handle the maximum and minimum subarray sums efficiently. Similarly, inefficient space management can be a problem. For example, storing intermediate subarray sums or absolute values can increase space complexity, while Cadon's algorithm can solve the problem in O1 space. For interviews, the key pattern to recognize is that this problem is essentially an extension of the maximum subarray sum problem. By running Cadon's algorithm twice, once for the maximum subarray sum and once for the minimum subarray sum, obtained by flipping the signs of the array, you can compute the result efficiently. The final answer is the maximum of the maximum subarray sum and the absolute value of the minimum subarray sum. This approach achieves an optimal time complexity of n and uses constant space. To reduce errors, it's important to clearly explain how absolute values relate to the problem constraints. During interviews, this clarity can help you avoid mistakes and demonstrate your understanding of the problem. Additionally, testing your solution with small, manageable examples is a good way to verify correctness. If you're looking to further solidify your understanding, there are several related problems you can practice. For instance, LeetCode 53, maximum subarray, is a classic example of Cadon's algorithm applied to find the maximum subarray sum. LeetCode 209, minimum size subarray sum, focuses on subarray manipulation and can help refine your skills in working with subarray constraints. LeetCode 560, subarray sum equals k, introduces cumulative sums and hash maps, which are useful techniques in array problems. Finally, LeetCode 152, maximum product subarray, is similar to this problem but focuses on products rather than sums, and can help you adapt your approach to different variations. Now, let's briefly discuss some alternative approaches. The brute force method involves computing the absolute sum for all possible subarrays. While simple to implement, this approach is highly inefficient, with a time complexity of n superscript 2, or even n superscript 3. Another option is to use prefix sums. By pre-computing cumulative sums, you can calculate subarray sums more efficiently than brute force. However, this approach increases space complexity to n, which may not be ideal. The most efficient approach is the two-pass Cadon's algorithm. By running Cadon's algorithm twice, once for the maximum subarray sum and once for the minimum subarray sum, you can find the maximum absolute value in n time with O1 space complexity. This method strikes the best balance between simplicity and efficiency, making it the optimal choice for solving this problem in competitive programming or interviews. Great job! To recap, we solved the problem by applying an efficient algorithm with n time complexity. Key takeaways include the importance of Cadon's algorithm and handling edge cases effectively. Thank you for watching, and I hope to see you in the next session. Keep practicing and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!